Good morning, class. Last time we actually solved problem 1.6 of this lecture, and we answered the following questions on the balance properties PB, MB, and EB. So I think we have finished solving this problem, but as I look into the solution, I found one slight error here. I have sent you the uncorrected file. So take note of the value of C1 in our discussion last meeting. We forgot to subtract a correction factor. Okay, so this is actually a correction for the displaced concrete. Okay, so remember that when we subtract 0.85 FC prime, we are actually trying to compensate on the displaced concrete, which is the space, no? The volume and the area of which is displaced and accommodated by the air of the steel. That's why there is a negative 0.85 FC prime here. But take note that this is only applied when you have a compressive force. Okay, when you're still force is actually compressive, just in this case it's C1, so we need to apply a correction factor. But when the steel is in tension, we do not make any correction, so this is just a simple Fy. That's why last time I actually have same values here. Since AS1 is equal to AS2, we get the same value here, and today we are correcting the final answer, which is no longer equal to this tree here. Okay, so these are the corrected answers for problem 1.6. Okay, I'd like to give you a table solution which is similar to the plastic centroid solution. Okay, so this is now a tabulated solution similar to the determination of the plastic centroid. Okay, so this table constitutes a larger workspace. So I have added actually this column here, which is the distance. Okay, I also added two columns here. Instead of having only one stress column, we have actually three columns for stresses. We have the computed stress. So this first stress here is actually a computed stress, which is based on the formula Fs is equal to 600 C minus the I all over C. Okay, so that's the formula here. For the maximum stresses, the formula is simply a comparison between your computed Fs and Fy. Okay, whichever is the bigger value, let's say here, where computed is 458, if this exceeds Fy, then I can only use Fy, which is 345.58. So is this, we only take the absolute value in terms of comparison, okay? Okay, note that these are comparable only with respect to their absolute values. So the absolute value of 345.58 is actually equal to 3.5.58, which is Fy. So I will use now uh, the stress to be negative 345.58. And the corrected stress, notice that the concrete has no correction. Steel 1 has a correction, so this is subtracted by 0.85 FC prime, so with correction. And steel 2 has no correction also because it's in tension, okay? So remember that when your stress Fy is in the compression, there's a correction, but in tension there's no correction. So the distances here are actually computed on the basis of the centroid. Okay, so this is actually your beta 1 CB over 2. Okay, balance. So this is a subscript. This is not a width, no? So this is simply C balance. Okay, and these are the D1s and the D2s. Okay, so how do you get now the force? You simply multiply the corrected stress with the area, and this moment arm is actually obtained by xp minus di. Okay, where the first here is actually beta 1 cb over 2, and this is simply okay, xp minus d1 and xp minus d2. So that's how you compute these two here. And then if I want the moment, I will simply multiply the force and the arm. I get these moment values here. Okay, take note of the sign. This is negative negative, therefore this is still positive. You add up to the force, you get your PB. Okay, this is your PB, and you add up to the moment, you get an MB. Okay, so finally I simply divide MB and PB, I get EB. Okay, so EB is simply equal to MB over PB. So I have the same result on a tabulated solution. So it's just the same. Okay, so whichever you want on your solution will be accepted, but I recommend, okay, this tabulated solution. Okay, let's now proceed with the conditions other than the balance conditions. So in most situations, the balance condition is not met because this is an ideal condition. Okay, so balance condition is ideal condition. And when this happens, the value of CB will either be greater or less than the actual value of C. And it is important to note that as a guide, the values of the parameters below may be predicted to help us formulate the correct assumptions and facilitate on the analysis. Okay, for C is greater than CB, the values of the following parameters may be predicted. Okay, so these are now the prediction. Your FSN, so the meaning of N here is the last, okay, still level. The last still level is always in tension, okay, so this is always in tension. And the first still level is always in compression. In between 1 and N, we don't know if it is subjected to tension or compression. Okay, that's why we can only predict FSN is predicted to be less than Fy, and FS1 is assumed. Okay, when there's a question mark there, it means to say that you have to check it. Okay, assume that this is greater than Fy. But if there's no question mark, you are assured of it. Okay, so let's say Pn is assured to be greater than Pb. E is also assured to be less than Eb, but Mn is assumed to be less than Pb. Okay, so after assuming, you have to check later if the case is okay. So for the C less than Cb values, the prediction are reversed. Okay, so your FSN now becomes greater than Fy, while FS1 is less than Fy, but this has to be checked. Pn is less than Pb, Mn greater than Pb, but still to be checked, and E greater than Eb. Okay, again, FS1 and FSN are the still stress at first and the last level. So this is what I mean by C equals Cb. So I have here my number one neutral axis. Okay, so that's the neutral axis at 1. C is equal to Cb. For C greater than Cb, so this is my plane section, and this is case number 2. Okay, so C is now greater, it's actually longer than Cb, and for C less than Cb, I have my neutral axis 3. Okay, and if we are going to look at the bottom part of it, for Cb is equal to C, this one, the ideal condition, your epsilon s is exactly equal to epsilon y. But for C greater than Cb, your epsilon s is less than epsilon y. And for C less than Cb, your epsilon s is greater than epsilon y. Which means that in case 3, your tension steel will actually yield. This is assured of yielding. Also in balance condition, your steel will yield. And here, it will not. Okay, yield. Okay, for the first steel bars, which is actually at the top portion, we have to double check. We're not assured of it, so we still have to assume and then check. Okay, so that is the way how to deal with it. So this figure illustrates the 3 possible conditions for the value of C, and note that the values of Fs in between 1 and n may be approximated only and cannot be predicted. accurately. Okay, problems on column analysis concerning cases other than the balance condition may be solved given the actual eccentricity E obtained by dividing mu by pu. So for cases other than the balance condition, the value of E is normally given, okay? Or if E is not given, your mu and pu will be given, where mu and pu are the factored moment and the actual load obtained from the analysis. So the objective is to solve for the value of C to locate the neutral axis, and it is still imperative that the value of xp must be solved if the section is not symmetrical geometrically and reinforced unsymmetrically. Although for sections with symmetrical shapes and reinforcement, the location of your plastic centroid is exactly at the geometric centroid. Okay, so take note of that. The procedure on XP determination is still important, but for symmetrically shaped and reinforced section, you don't need to compute it because your PC is actually the same as your geometric centroid. Okay, so let's try to solve now the same problem 1.6. By assuming an actual eccentricity of 300 millimeter, which is greater than the EB that we got from problem 1.6 a while ago. Okay, so this is actually less than, your EB is actually less than E actual. Okay, so or your E actual can also be greater than EB. Okay, so these are just the same. EB less than E, E greater than EB. So if we predict it here, what will be our predictions on C? So you just take a look on your value. When E is greater than EB, then C is less than CB. So this is our prediction. Because E is greater than EB, so 300 is greater than 250 something. Okay? So 240, oh, sorry, 242.502. Okay, so we are on this case. So C is less than CB. So these are now our assumption. FSN greater than FY, PN less than PB, MN greater than PB. But this has to be checked. E is greater than EB. And FS1 is less than FY. This is still to be checked. But for me, I will, since this is questionable, I can predict FS1 greater than Fy. So that FSN and FS1 will both yield. So that's our assumption. So actually, you can change your assumption. This serves only as a guide for you as beginners. No? But experience will tell a lot sooner or later. Okay, so let's not use a tabulated solution because it's very difficult to do it since your C is unknown. We are now going to determine the value of C or locate the neutral axis. Small c, I'm referring to small c. For the capital C for concrete, the formula is the same. 0.85 F prime C beta 1 CB. Where C is unknown, so everything is given. FC prime, beta 1, and B are given. So you just multiply everything, you get 5243Z. Okay, for the moment arm, notice that there's a change in the formula in the moment arm because we are trying to take summation of moment about the plastic centroid. Okay, so if this is our figure here, Okay, and the eccentricity is somewhere, let's say, here, assuming that this is your eccentricity from the plastic centroid. Okay, so my xp is here. So if I make use of summation of moment at this point, the not the plastic centroid, but the force Pn. So let's change this moment here. So this is not about the plastic centroid. So this is about the force. Okay. So what will be my distance here? Okay, so if I take moments about PM, my moment arm for the steel, I have a steel here at D1. Okay, so the distance of this steel to the P and L is simply E, the total, minus XP, and then I add the D1 there. Okay, so in general, my formula will be in the form of an E minus XP plus DI, where DI for concrete is simply 1/2 of your beta 1C. Okay? And your D1 and D2 for the two steels are E minus XP plus D1 and E minus XP plus D2. Okay, substituting the values for E is 300 minus 250, okay, plus. So these values here are obtained by dividing 0.85 over 2, so this is 0.425. So 300 and 250, we have a fixed 50 here. 50 plus 0.425C. This is also 50 plus 65, which is 115, and 50 plus 435, which is, okay, 485. Okay, multiplying now your CC multiplied by arm, C1 multiplied by this arm, and T2 multiplied by this arm, we get your equation in terms of C, okay, 5243C multiplied by 50 plus 0.425C plus 400, 300 times 115. So I just multiplied here and then multiplied it. Don't forget the sign. Okay, so this is equal to 0. And then you can distribute and solve it in the form of a quadratic equation. So this is a quadratic equation in C. So I'm using MathCAD. That's why I can simply use this block tool or the block solution. I get your C becomes the unknown X, which is 215.832. Okay, so again, as I have told you, after locating the value of C, we need to double check the results. So it is important to check assumptions after getting a value for C. Okay, so first the assumption is that the steel in compression yields, so this is FS1 600, this is actually equivalent to C, okay, or X is actually equal to C. C minus D1 over C, and 600 C minus D2 over C, you get these two here. Okay, when you are comparing values for your Fs and Fy, always use the absolute value on the comparison. So 419 is greater than Fy and 609 is greater than Fy. Therefore, both steel will yield. And we have to neglect the sign when comparing. I'm stating that when comparing, you neglect the sign. But when you are computing, you don't neglect it. Okay? Don't neglect when computing. Okay, so for the check of results, we have CC using the formula 0.85 FC prime beta 1 CB. So knowing C, we can now solve CC. So we get 1132 times 10 to the 6, and also XP minus beta 1C over 2. We get 158.271. Okay, remember that our arm here goes back to the summation of moment at the plastic centroid. Okay, yung kanina summation of moment about PN, ito naman about the plastic centroid. Okay, for still at level 1, the compression yields, the sign is positive. Okay, Fy must be positive with correction. So there's a correction here which is 0.85 Fc prime. So for still at level 2, the tension yields, the sign is negative without correction. So there's no negative 0.85 Fc prime there. So xp minus d1 and xp minus d2 are readily solvable, and that those are 185 and negative 185. You have to carry the sign for those, such that your Pn now will be simply the sum of all of these values here, which is 1.107 times 10 to the 6, and Mn is simply obtained by multiplying Cc times this value there, C1 times this moment arm here, and T2 times this moment arm here, which is simply these values in this expression, and this equivalent to 3.32 times 10 to the 8. So dividing Mn and Pn, you yield now 299.95, which is very, very close to 300 millimeter, which is given. Okay, so this is the given eccentricity. So there must be at least fairly close to each other. Okay, so approximately equivalent. Okay, so this is just a check. The final answers there are these ones here. Okay, so that ends my lecture on cases other than the balance condition. I will be giving you a problem set, and then next week you will be having your quiz on columns. Okay, so next I will be scheduling that next week para you have time to figure out your concerns about the lecture. Okay, so thank you very much for listening. So I'll see you on the next lecture.